It says we're recording, so we'll see. I would love to introduce Mark Bottoff. You're going to see up here his bio, all sorts of information about him. I was going to read out the third bullet point, and then it was so complicated, I couldn't even read it hardly. So take a look at it, but I read some interesting things about him. First of all, he has a PhD in physics, or actually astrophysics. He has been with Southwestern University here in Georgetown since 2002, and he's been an associate professor since 2008. And some of the more fun things, I mean, he just didn't decide he liked astronomy when he was 25. When he's always had a love of science and astronomy. One evening, as a young teen, he looked up and noticed a bright star in the sky. However, when he viewed it through his small telescope, he realized that the star was actually the planet Jupiter. So the very next day, he checked out the Time Life series book, The Universe, from the school library, and he read it cover to cover. So he was hooked from then on. His first job was, guess what? Working in a telescope store. And what did all of his money go toward? Buying a good telescope. So he went to see his first total solar eclipse in 1979, and then in 2017, when they had a solar eclipse that I actually saw also, he and his wife packed up their dog, 2 cats, in the back seat, along with the telescopes, and went and drove 1,500 miles to see this total solar eclipse in Wyoming. And somebody asked him, was it worth the 3,000-mile round trip for 2 minutes and 13 seconds of total metaphysical bliss? And he said, absolutely, it's truly life-changing. So he already has on his calendar April 8th, 2024. Guess what that is? It's our next total solar eclipse here in the Austin area. So we've got Mark here to tell us probably not any more about total solar eclipses, but even more fascinating, black holes. Thank you, Mark.
Thank you. I'm wearing the lapel mic. Can you hear me in the back? Can you hear me okay? Great. So Peter's going to bring up the slideshow and we'll get going here. All right, so I'm here to talk to you about supermassive black holes for fun and not for profit. So the question is, what does the scientist mean by fun? So a fun to a scientist means a challenge. Fun to a scientist means that you try to understand more deeply what the universe has to say from the data that you collect. And it can be exasperating and challenging, but that's what a scientist means by fun. I've been funded through National Science Foundation to do postdocs. I've even evaluated grant proposals at National Science Foundation in Arlington. I've done it a dozen times. So I've helped to dole out your federal tax dollars. But all of this work I did for the learning, and I wasn't funded on this work, all right? So it's for fun, truly, intellectual pleasure in a scientific way of thinking about it, not for money here. So I'm supposed to try to tell you things about supermassive black holes, so I'm going to try to do that. I want you to just relax. There's no test at the end of this. I have a wide range of talents when I give a talk like this. People who have a very technical background, a lot of the amateur astronomers know a lot from reading Sky Telescope. Maybe some are retired engineers, so they have some quantitative skills, and others who don't. And just like looking up at the nighttime sky. So I have to split the difference. So if every now and then a number appears or a short little equation, don't worry about it. Just listen to my calming voice and we move on from there. So are we all good with that? Yeah. Okay, so let's go ahead and get started. You're looking at a picture of the effect of a supermassive black hole. You're not looking at a supermassive black hole. It's too small in this picture. You're looking at a composite picture of a galaxy that's, oh, maybe 100,000 light years across and 1 trillion stars. That's the white blob. And superimposed on that in red, which is false color, is a picture of the radio sky. We astronomers look at the sky in different kinds of light. Radio waves are light. Microwaves are light. Infrared light is light. Light that we see is light. Ultraviolet light kind of gives you a sunburn is light. X-rays, like you get when you go to your doctor's office, is light. And gamma rays, very, very high energy. Well, don't go near any nuclear explosions. But at any rate, all of those are light. And astronomers learn about the universe not just from one color or color band, if you will, but from all sorts of different kinds of light. So in this picture, we see superimposed on this galaxy in white, this pink, which is radio, a very fascinating thing. You see these double beams of pink shooting out from the center of this galaxy. This is the telltale sign that in the center of this galaxy, there is a supermassive black hole. So, supermassive black holes are the great white whales of astrophysics. I kid you not. You see an old movie like Moby Dick with Gregory Peck in it, and they ask him, why do you chase the great white whale? And he walks back and forth and he says, it's because he taxes me. He taxes me. And he goes on to say, not only does it tax him that such a thing could exist in the universe, but also he knows that behind that thing is the actual thing. For him, it's the evil that's causing the white whale to do what the white whale does. For an astronomer, we see the effects of the black hole, but the thing that's behind it is what we're really looking for. And only now, this year, in the last 2 years, have we finally seen the beast. Okay? But there are so many interesting effects from which we've learned so much about supermassive black holes that it's worth looking at. But it's vexed and taxed astronomers for 70 years to try to figure this out, what's going on with these objects. So it's an interesting mystery story. So here's a very brief history. In 1943, during the Second World War, Carl Seifert was using the 100-inch Hooker telescope on Mount Wilson, excuse me. And it looks like a freight train. If you can imagine a big iron girder thing. It was with the largest telescope of its time, 100 inches in diameter. That, by the way, is about the size of the Hubble Space Telescope. And he used the fact that we had blackout conditions over Los Angeles because it was the war to take images of some galaxies that had anomalous behaviors in their centers. These became known as Seifert galaxies. And the anomalous behavior was quite a head scratcher for astronomers of the day. They were bright. The light seemed to come from something that wasn't stars. It sort of looked like a cloud of gas light, but it was too bright for that. So it was quite the mystery. Then, as technology changed after the Second World War, of course, radar was a big thing that helped the Americans win the Second World War, especially in the Pacific. The radar instrumentation was turned towards the sky, and we began to detect radio waves from space in greater detail. And we looked in the sky, and we saw strange things like that pink lobe thing I showed you at the very beginning. And people said, well, what's causing that? What would cause this big double mushroom all over the sky, dozens and dozens of them, all right? So they looked, they said, where is the source of this radial light coming from. So they looked, and all they could find was a little tiny pinprick of light on the sky. It looked like a star, but it wasn't a star because stars don't have these big flowing orbs of gas shooting out from them that they detect in radio wavelengths. So they weren't stars, so they called them quasi-stars. And they were radio sources, so they became known as quasi-stellar radio sources, or quasars for short. So if you hear the word quasar, that's what they're talking about. In fact, in that Time Life series, The Universe, that shot me off into astronomy, one of the very last things in the book was talking about the mystery of quasars. And here I am, a lifetime later, and we finally cracked it, and we figured out a lot about them. Well, the big revelation came in 1963 when an astronomer named Martin Schmidt in the lunchroom of the university was talking to some astronomers and said, you know, we've got these strange looking light patterns from these quasars, and you can't figure out what they are, and I'll take a look at them. And he took a look at them and he said, you know, those things look like the signal of hydrogen gas, but they're all not in the right place. And that made everybody take their breath away, because what they realized was that these things were very far away, and I will explain in greater detail in a second. But that tipped it off. They are a great distance, so even though they're dim little star-like objects in the sky, because of their great distance, they must be very, very bright. And theoretician Lyndon and Bell suggested, finally, that maybe these are supermassive black holes. Right, so this is the first inkling of it in 1969, 1970. I remember being a child in elementary school, and I had these books called Highlights, you know, these children's books. And inside there was a picture of a star with a smiley face on it. It sort of takes its lip and it puts it over its nose and it swallows itself up. That was the first time I had ever heard about anything like a black hole, that there could be a star or something that swallows itself whole. And I just thought, that's kind of weird, but I was just a kid. You know? At any rate, once the association was made that these objects were supermassive black holes, very large black holes, then they started looking for these things in detail. They started doing surveys of the sky using optical telescopes, that is light that we can see from the ground. They found many, many of these objects. Carl Seyfert had just found a few dozen. The radio catalogs had found a few hundred, but these optical surveys started to find thousands of these things. And we now know there are millions and millions of these things in galaxies. Okay? So the problem was, of course, energy. These things are very energetic, and very energetic things usually require energy that's beyond what can make it through Earth's atmosphere. We are very lucky. We get sunburned by a little bit of ultraviolet radiation from the sun, but most of it is filtered out. The X-rays from space are filtered out, so we're protected a lot. But to understand these things, you have to understand these energies as well. So we built space telescopes. We finally had the technologies in the 80s and 90s to do that. And so we could finally see the driving source of what caused quasar phenomena. And then by the 2000s, large robotics telescopes were turning these things up by the bucket loads, tens of millions of objects that have been found in the sky that are quasars or their baby cousins called Seyfert galaxies. And they're everywhere. So if they're everywhere, they're an important aspect of the universe if we're going to understand the universe that we live in. So let me just say in a nutshell what they are, and then I'll go into some more pictures here. So quasars and Seyfert galaxies are what we call active galactic nuclei. So active means that they're an intense light source. Like I said, all kinds of light. Galactic means that they're in a galaxy, great island universe of stars, 100 billion stars. Nuclei means The center, so these are active light sources at the centers of galaxies. So we call them AGN for short. And with every one, we have seen that there is a supermassive black hole at their centers. Every one, right? How does light come from a supermassive black hole? Everybody says, well, if it's a black hole, it swallows everything up and no light can escape it. That's what it said in the Popular Science magazine I read. That is true. But the matter has to get in there first. And there's sort of a traffic jam that scientists call an accretion disk that can become superheated. It's a terrible traffic jam as material falls in. That traffic jam of material before it falls in gets so hot, it's heated to incandescence, and that's the light that we see. All right, so the light is liberated from a tiny region. Just how tiny on an astronomical scale, you'll see, and that should take the breath away, that so much energy could come from such a small parcel of space. And the average quasar is so far away that they appear dim, but they are intrinsically bright. They're the brightest things in the universe. They're the most powerful natural engines in all of nature. So today, we know that every galaxy has a supermassive black hole in it by various means. So here's a picture of the Hubble, one of the Hubble Deep Field pictures. Except for that bright point right there, which is a nearby star. Oh, yes, I got a pointer, which is a nearby star in our own galaxy. Every little fleck of light that you see there is a galaxy. Every one. Throughout the entire universe, let me rephrase that. Throughout the entire visible universe, there are maybe 300 billion galaxies. Think about that. There are 300 billion stars in our own galaxy. For every star in our own galaxy, think of a galaxy that each has hundreds of billions of stars. And each one of those, if they're a galaxy of average size or bigger, they have a supermassive black hole in them. So there's an important connection in the formation, history, and evolution of the universe that ties supermassive black holes to the galaxies that they live in. And that is an ongoing area of research. That's a mystery that has not been solved yet. All right, an overcrowded slide, but it's the cartoon version of this thing. So let me give you the cartoon version. In the center of every galaxy, this white egg thing represents what we call the central engine. It's where the black hole lives. And a flat, hot disk of material called an accretion disk. That is where all the energy comes from. Light is so intense from that region. And when I say light, once again, I don't just mean visible light. I mean X-ray radiation, gamma ray radiation, etc., that it illuminates gas that is in its vicinity. So all of these little teal flecks here are gas near the big white egg. All right? That gas gets illuminated and fluoresces as a result of the higher energy light that's being given off by the white egg. And we can see that gas, and that gas is in motion, and that gives us clues about how heavy the black hole is, the state of motion of the gas around the central engine. These are things that are still being worked out, the details of how gas falls into the black hole through the accretion disk and how that's managed. That's ongoing. Much work is being done on that, and I participated in some of that work. Well, every engine needs a gas tank, right? Can't drive your car without a gas tank, unless you have an electric car, but if you have an electric car, you power it up yourself. So at any rate, the fuel cell is right here in this orange donut. It's farther away, so it's cooler, so it's a big donut-shaped cloud called a molecular torus. That supplies the black hole over time. Now, because it's a donut and it's dense and dusty and cooler, a lot of light doesn't get through it. So if I'm a cloud in the galaxy that's in line with the donut, I don't see the light from the black hole on the inside. So these clouds are unaffected. But outside of that, if I'm looking down into the donut, the clouds of the galaxy that happen to drift in the way do get illuminated, and they get excited and they emit light too. And in fact, if you're exposed here, not only do we get the intense light radiation from the accretionist of the supermassive black hole, but we get strong winds which push against this material. And we can't see resolve what's going on here, but we can actually see these clouds getting pushed on by the very energetic ancient inside. And the black hole creates a jet. Now, the reasons for that jet, I'll just hint at in the next couple of slides, that this collimated jet that formed that big, long pink line that I showed you in the very first slide, slams into gas in between the galaxies. We think that galaxies, at least there's nothing between galaxies, but there are. And so a big shock wave happens there, and you get a big puff of radio burst from this beam of light going off in both directions. It's a very complicated thing, right? I mean, a star is this round ball of incandescent gas with fusion going on in the core. Maybe it's rotating fast, maybe it's not. It's simple by comparison to this, which is why it took 70 years to figure this stuff. All right, if you look at the central engine itself, and this of course is a cartoon, what we see is a swirling disk of gas, and it swirls around the central engine, and close to the central engine, the supermassive black hole is where the powerful jet is formed, which throws things out. That jet is necessary, and we observe jets all over the universe, not just with supermassive black holes. So, if you've ever watched ice dancers, right? And a figure skater is going along, and she comes in, and she brings her arms in after swinging her leg out. What happens? Spins faster and faster, right? And that's called angular momentum. It's turning motion, and something tends to keep turning in that direction unless friction slows it down. What happens if there's a ballet dancer? The partner's there, and the ballerina comes up, and she double takes her leg out, she swings it off to the side, and then brings it in really quick. Same thing, she turns really fast, yes? So it turns out that if something's turning really fast, it'll go so fast that it won't be able to fall in any farther. So if you're going to grow a black hole, if you're going to grow a solar system, if you're going to grow a planetary system, you have to get rid of some of that turning motion. Otherwise, the material cannot collapse under gravity, say. And these jets do that for us. So it's these jets that we see are nature's way of throwing away turning motion so other material can fall in. Now, I wanted to mention this because everybody says, oh, well, not everything falls into a black hole and disappears from the universe. That's not true. Some matter falls in, but it's at the expense of other matter being shot out. And that's what we see with these jets. If you get a little bit closer, you see where the jets form. They form very close to the black hole indeed. And there is open debate about what the jets are caused by. And I'm definitely in one camp because I wrote my PhD on it. So I'm kind of married to that. Some people think that it's magnetic ropes. All right. So imagine taking a bunch of wheat and gathering it together. As you gather it together, the wheat stalks get crushed together, right? And you get all these parallel straws. So the idea is here that there's magnetic fields, and as material falls into the black hole, these magnetic field lines get crushed closer and closer and closer together, get very strong. And gas gets stuck on those. Now, what if I have a bead on a wire? If I were to swing the wire around my head, the bead would go flying off, yes? Sure. Well, that's what they think is happening for the people in the magnetic camp. The people in the hot gas camp say, well, it's just so bright there. The light is so bright that it pushes on the material up and out of the donut in both directions. So the war goes on. But I think the magnetic people have won. So I told you a lot of crazy things, right? I just told you a bunch of insane, crazy things. So how do we know that any of this is true? Well, first of all, we see these big lobes, like I showed in the first picture. See how narrow and collimated that beam is? The galaxy that this is in is right there. So something had to be very small and powerful to maintain a beam that could shoot 1 million light years out into space. And you see in this picture how there's no beam on the other side? There's nothing there? Well, there is too something there. It turns out that if the beam is moving really fast, like almost the speed of light fast, then most of the radiation is in the direction, most of the light it gives off is in the direction it's going. So the back one is pointed away from us. The one on the right is pointed towards us. Just the fact that we see an on and off in that picture tells us that that material is traveling at a substantial fraction of the speed of light, and only something very energetic can do that. And the fact that it's so collimated, so it's such a fine line tells us that it comes from a teeny tiny region. All right, and they're bright too. So on the picture on the left here, which is the galaxy that's in our own galaxy, which is the star in our own galaxy, and which is the quasar? Can you tell the difference? I can't tell the difference. And maybe if I inspected it really carefully, I looked it up once, I actually forget. I can't tell that one's a star and one's a quasar. That was the problem that we had up until the 1980s, when we had A, space-based telescopes, and B, when we had ground-based telescopes that could compensate for the Earth's vibrating atmosphere. And we could finally see things really sharp. And you can see in this picture here, here's a quasar. It's so bright that it's completely swamping the galaxy that it's in, but you can't see parts of the galaxy. That's telling you that this quasar is so bright that the light it's giving off is rivaling the brightness of every star, perhaps 300 billion stars in the galaxy that it resides in. And yet, it comes from such a small space, in this picture, less than the size of 1 pixel, that is very high energy and very compact. Oh, by the way, this cross piece here, that's not a jet, that's an artifact of telescopes. A lot of telescopes have a cross piece with a mirror beam. All right, so they are far away, they're very bright, they're brighter than an entire galaxy, and they are always in the centers of galaxies. We've never seen one that's very far off from the center of the galaxy that it resides in. So here's 2, all right. Romantic names, right? NGC 5548, NGC 3277. NGC was a catalog, a new general catalog of nebulae created in the Victorian era, and it was a compilation of other catalogs that previous astronomers had put together, and they're sort of go-to usual suspects. There's about 7,000 of them. No, I have not seen all 7,000. But both of these galaxies, we can compare. Here in NGC 5548, see how washed out it is? See that spike there? That spike is due to the fact that the camera is so overloaded that it's causing the pixels to flood. That's too much light there. Over here, you don't see that in this galaxy. The one on the left is an active galactic nuclei. You're seeing light, about half the light there is coming from a supermassive black hole of about 30 million solar masses. Okay. And you say, okay, well, I don't see any light here, so there's no supermassive black hole in that one. Wrong. There's a supermassive black hole in that one too. It's just that it's not feeding right now, and they only get bright when there's material there to fall into the black hole. Well, Andrea Ghez won the Nobel Prize in Physics in 2020 for this discovery in our own Milky Way galaxy. Using telescope that can see in infrared light, she and her team were able to peer to the very center of our own Milky Way galaxy, and over a period of a decade, she followed the stars at the very center of the galaxy, which is where those little yellow arrows are. There's no spectacular amount of radiation coming from there like in quasars, but when you follow the little tiny dots there, which are basically red giant stars, they loop around the central source on the time scale of a decade. Based on that, about a dozen stars following them for a decade, she could work out what the mass of that thing was that they were looping. And it turns out that it was 3 million solar masses. So we have a baby supermassive black hole in our own Milky Way galaxy. Why ours is small and other galaxies are large, that needs to be worked out yet. But the point is that NGC 3227, that didn't have a great big flare of light in the middle of it, it's got a supermassive black hole in it. It's just not active. So every galaxy's got one. All right, so what kind of light? How far are these things away? How bright are they? How small and compact are they? What's the structure of the central engine? What's its environs like? And how does the gas move? These are all questions that are actively being worked on by astronomers. For instance, there's a galaxy called M87, big elliptical galaxy. If you zoom in, you see that from the very core of the galaxy, there's a jet. If you zoom in some more, you see a molecular torus. And just recently, the ALMA project has finally seen the shadow of the supermassive black hole in the very center of this using a microwave interferometer, the ALMA array in Chile. So this is the first time we've seen the shadow of a black hole. That's pretty amazing. All right. So, ugly graph here, but let me just explain in words what it says. The light from a black hole, the light from a quasar comes from the entire electromagnetic spectrum. Everything from radio waves all the way up through X-rays and gamma rays. So just think of this as light frequency going from a longer wavelength light up to shorter wavelength light. So X-rays here, ultraviolet here, optical here. And we see in this curve that there's light all over the place. It's all over the spectrum, and that's what makes it hard. Because a star, it's like a bump like that. All right? They're easy by comparison. So I show this because there are many physical processes happening all at the same time, which is a huge challenge to the best astrophysicists of our times to figure out. It requires huge teams, both observational and theoretical, to try to work and fight, debate, try to figure out what's going on. So I'll just call attention to these little spikes right here. These little spikes I'm going to come back to, they're called emission lines. When atoms are excited to emit light, they do so at specific wavelengths or colors. Why a neon sign looks different than an argon sign, it looks different than a hydrogen gas, arc line, etc. And we use that to determine the chemical properties of things in space, determine the state of motion. Well, there's a lot to them, so I'll come back. All right, now quasars are intrinsically bright, but because they're so far away, they appear dim. So in this cartoon here, we've got the learned astronomer with his little dunce cap on, looking at a quasar source. The nearest bona fide quasar is an object called 3C273, third Cambridge catalog, the 273rd object in it. These were radio sources in the sky. So, what this shows here is that if you double the distance, you spread out the light 4 times as much. You triple the distance, you spread out the light 9 times as much. So the further away something is, the dimmer it appears. Everybody knows this. You look at a street light a mile away down the road, it looks pretty dim, right? You're just under the street light, it looks really bright. Well, if we could figure out how far away these things are and see how bright we observe how bright they appear to be, then we can reverse engineer this and figure out how bright they really are. And when the answer comes, it's just stunning how bright these objects are. And we can figure out how far away things are thanks to another great discovery in the 1920s by Edwin Hubble of the Hubble telescope, named after him, was that the universe was expanding, right? So there was a beginning to the universe. The universe is expanding. if everything's uniformly expanding, it turns out the farther away something is, the faster it's moving. Think of a raisin cake, right? You gotta put some dough in a pan, and there's two raisins next to one another, and there's one a little bit further on down. Let's suppose the dough doubles in size as you let it rise. So the first one goes 2 inches, but the second one goes 4 inches. So the farther away something is, the faster it's going, but instead of raisins, they're galaxies in the universe. That's how it works. So Hubble discovered this relationship, got his picture on Time magazine, won the Nobel Prize, etc., and came up with a law called the Hubble law, meaning simply the farther away something is, the faster it's moving. And for about 70 years, we didn't know the fudge factor. We didn't know how much faster for how much farther, but now we do, so we can really get the distances down to this thing. For instance, in the last 10 years, 15 years, we've moved from an era where we knew very little about the origin and evolution of the universe to knowing a great deal. And that's thanks to satellites like WMAP, which map out the details of the gas of the early universe. Each one of these bumps in this all-sky map are clusters of galaxies that are ultimately going to form, but it's light coming from so far away, the light that we're seeing, we haven't seen them form yet in the image. But we can look at these lumps and bumps in this picture and figure out how fast the universe is expanding. So we can use the Hubble law to figure out this thing. Well, okay, so now we've got a scale, and Martin Schmidt told us that, gee, these lines look like hydrogen, but they turned out to be redshift. I don't know about you, but when I was a kid, I didn't live that far away from a railroad track. Anybody near a railroad track? You know when the train comes and it starts blowing its horn at the crossing? And when it's approaching the crossing, that train horn sounds really shrill, doesn't it? It's really, but after it passes, it's a lower tone, isn't it? The train, as it's coming towards you, giving off sound waves, the sound waves are crushed together. That's why you get a higher frequency. When it's going away from you, the sound waves are stretched out. That's why you get the lower frequency. Light does the same thing. If a light source is going towards you, the light fronts are crushed together, so you would actually see bluer light if it's moving fast enough. But if it's moving away from you, you see it as redder light. So when we look at the light patterns from these quasars that happen to be due to atoms of hydrogen, we see them all shifted towards the red. And so we can use that information to figure out how fast it's moving. And then fold that into the Hubble relationship and figure out how far away it is. And the answer is just breathtaking. So let me just cut to the chase, all right? So the nearest quasar has a redshift of 0.51. Okay. So what does that mean? It means it's going away from us at 15.8% the speed of light. That translates into 47,000 kilometers per second, or for good old American units, 105 million miles per hour is the recession speed. And it's just because the universe is expanding. Quasar 3C273 is being carried away from us, or we're being carried away from it as a result of the expansion of the universe. But the magic is that we can use Hubble's law to figure out the distance. And when we figure out the distance, that's another thing that takes your breath away, is 2,200 million light years. In other words, 2.2 billion light years. So remember, the universe is a time machine. When you look out into space, you don't see the universe as it is, you see that it is as it was, right? Because it's taking time for the light to get to you. You take a glance at the sun as it's setting. Don't ever stare at the sun directly. Right? That's 8.3 minutes ago. You look at the moon, that's 1.2 seconds ago. Right? You look at the nearest star, look at the sun, Alpha Centauri, that was 4 years ago. You look at the Andromeda Galaxy, it's 2 million years ago. It's like people are sending you text messages through space, right? And you're just getting them on your phone because it took that long to traverse this great distance. So this is 2 billion light years away. That's 7 times the amount of time from when this Dimetrodon was climbing around on the Earth. So 7 times further back than the first dinosaurs crawling around on the surface of the Earth. That's a frighteningly long time ago. So, gosh, but we can still see the thing. If it's so far away, it must be incredibly bright. So now we can work out how bright it is. Because we got the Hubble law, we got the distance, we can see how bright it is. I've seen it with my own eyes in a small telescope. You can chase down, astronomy people, 3C273 in a 6-inch telescope. With my younger eyes, I could see it with a 4-inch telescope, just barely. That's the furthest thing that you can see with your eyes. Telescope is needed, but you can see it. Something 2 billion light years away. All right, so now just hold on to your hat. How bright is it? It is, punchline, 26,000 billion. So if every billion, do that 26,000 times, it is 26,000 billion times brighter than our sun. This is just stunning. I mean, how does something get so incredibly bright? It's crazy. All right, so you need fuel to do that, right? You've got a flashlight that bright, you better have big batteries, right? It turns out this particular object has to eat 15 M circle per year. What is M circle? That circle dot is solar masses. So for this thing to work, it has to consume the equivalent of 15 masses of the sun every year, and it does that for millions upon millions upon millions of years. Now, when I see all your squinty eyes going like, what? Now you know why it's so interesting to us, isn't it? All right, so the light that is emitted from the little white egg illuminates not only out into outer space, but the gas that's nearby it. That's where we get some interesting things. So here's another picture of these spikes. And these spikes are the spectrum. So here we have magnesium, here we have hydrogen, here we have oxygen. And so each of these spikes are being caused by the high intensity light from near the accretion disk of the black hole, illuminating gas further out. And you can see, oddly enough, that some lines are spiky and other lines are broad, so there are 2 different regions. One called the broad line region and one called the narrow line region. So there is a narrow line and there is the broad line. And just as we can use the Doppler shift to tell whether or not something is going toward you or going away from you, we can use the Doppler shift to see, okay, some of the gas is going toward you and some of the gas is going away from you. In other words, this pyramid shape at the base is telling you that the gas is swirling around, moving in the vicinity of the black hole. How fast is it moving? Well, this is about 5,000 kilometers per second. Some of the gas is moving at 50,000 kilometers per second. This is about 500 kilometers per second. So this gas must be further out than this gas. So this explained a big mystery that astronomers had. It seemed like there were 2 flavors of quasar, the type 1 object and the type 2 object. In type 2 objects, we saw both the broad lines and the narrow lines. In type 2 objects, we only saw the narrow lines. And what that meant was that with type 1, we could see down into the black hole where the swirling gas is going really fast and slower further out. Whereas if we're looking at it from the side, we can't see into where the gas is swirling really fast. We can only see the slower gas further out. And that gave us the information that we're dealing with the molecular torus, something thick that blocked our view in a lot of cases. In 1980s, we weren't sure about that. Now we're very sure about that. And we've even mapped out the toruses around some of these objects as part of the study. So, that was good timing on my part. So what about my part in this great game of studying black holes? Can you do it with small telescopes? And the answer is yes, because they're so incredibly bright, even though they're far away, they're accessible with a modest-sized telescope. The observatory at Southwestern, which is currently under repair, has a 16-inch telescope, but this kind of work could easily be done with a 12-inch diameter telescope. So if somebody wants to get into the imaging game, you need a telescope, you need an electronic camera, and special science filters. That was for the astronomy people over there. So they're bright, they're far, they're powerful. How big are they? That's the next question. And I like to use an analogy of echoes. All right, so we use light echo analysis to figure the distribution of swirling gas out. Imagine a campfire. All right, it's a dark night, somebody's got a campfire. You look down at the campfire, you see people standing there, and they're having a loud conversation. All right, they have too many brews or what I think. They're having a conversation. Right, but it's dark all around and you can't see the terrain around, but you know that there are canyon walls around. What are you going to experience? You're going to hear their voices, right? But their voices are going to go out and reflect off the canyon walls and eventually get to you. So you'll hear them and their echoes, yes? The same thing happens in the vicinity of supermassive black holes. Close to the supermassive black hole, material falls in and gives off a burp of energy. That burp of energy flows out and it illuminates the other parts that are near the black hole, sort of like the canyon walls, and then that light goes out. And so there is a delay between our initial burp and our echo. And I think this is best seen not in this figure, but in this picture. This is a cartoon of cross view of the accretion disk. There's a whole other mirror side on the other side. So imagine there's a burp, there's a black hole, there's a burp of light, and some of that light goes off to Earth. Some of that light goes off in a different direction. Some of that light skips off the swirling gas around the black hole, interacts with it, and it causes that material to give off its own light, and it heads off to Earth. Well, look, this distance is shorter than this distance. So that means that the light from this is seen by astronomers on Earth later than this. So there is a delay in the response. So if you put your two hands like this, and here's the actual response, and here's the delay, you can start shifting one relative to the other until you've got a pretty good match. And then you say, aha, that's how far away the swirling gas is from the central supermassive black hole. Or that's a simplified version of it, of course, but that's what we do. And so now we can figure out how big the region is. Here's some data that I helped take. All right, so the red crosses are from a space-based telescope. The blue dots are from ground-based telescopes. And the one pattern has been shifted relative to the other by 47 days, which means that the red region that's further out is 47 light days away from the black hole. So that now tells us how big the swirling tub of gas is that feeds the black hole in this particular object. Kind of camera that we use, again, a little nod to the astronomers here. It's a very old 60 camera that it does this job. And here's some papers that I'm part of. If you want to know what big science astronomy looks like, it looks like this. See all these authors, they're professors and graduate students. And here's one of my students who's now just got a PhD. And here's a guy named John Upton, who's a local amateur astronomer who helped me out. Here's another one. Look at all those names. It's big work to do a project. It's an international campaign. You need hundreds of people, both on space-based telescopes and ground-based telescopes, to get all the data together to get results, the results we now have. So in this particular study, these are my students. This one's now at A&M. This one is ACC. This one got his master's at Oklahoma. He's now teaching in Colorado. Right? At any rate, this is the data that they took. It was combined with other data as well as data from the Hubble Space Telescope. So big telescopes, small telescopes, it's a big tent, and it led to some interesting results. This is what one of our objects look like. So again, You can see that there's a galaxy that is particularly bright in the center. So this is the third observing campaign I was on. And you can see that there's a total wash of light here. So maybe the third half of the light there is not from stars. There's a lot of stars in the center of a galaxy. There's maybe 1 million stars per cubic light year, compared to maybe 1 per 64 cubic light years out where we live. Nevertheless, most of that light is not from stars. So here's David Oliphant on the left. Jonathan on the left, and David Oliphant on the right. And there's our workhorse telescope, about the size of a beer barrel. So with the size of a beer barrel telescope, we were able to probe a galaxy 230 million light years away with a 30 million solar mass black hole. Can be done. Now, back to the scale of things, because these things are just so off scale, pardon the joke there, that as I wrap things up here pretty quick, we need some scale. So imagine the galaxy that 3C273 is in, scaled down to the size of Texas. How small a region does the light come from? It comes from a region 10 feet across. At 26,000 billion suns worth of light. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The swirling disk of gas is that big, and the galaxy that it is in is the size of Texas. Does this give you a feel for the intensity and compactness of these objects? Yeah. All right, I'll move forward here. I'm way out. Sorry. All right. Well, can we see this swirling gas? And the answer is no. Even with the Hubble Space Telescope, we don't have the resolving power. What would it be like to try to see the swirling clouds of gas directly, which is why we need light echo effect? If you placed a 4-inch latte on the moon, that is the same resolution problem as trying to see the swirling clouds of gas around a supermassive black hole. That's the problem. So that's why we have to resort to the trickery of using light echo analysis to work out everything. So, jump ahead. From the speed of motion and now from the size, we can work out how massive the black hole is. We can equate the amount of energy of motion with the amount of energy due to gravity, and we can work out from that how big the black hole is. And the black hole in the 3C273 is 700 million suns worth of mass. But this is my second to last slide here, so hang in there. If you made the scale model 10 feet, and the whole galaxy is Texas, the size of that supermassive black hole is 1/4 of 1 inch on this scale. Just think about that. In physical actuality, you could put it within our solar system. The black hole would go out to about, the orbit somewhere between Saturn and Uranus in terms of size, but that is still very small. So, conclusions. Oh, happy we're at the last slide. Supermassive black holes and AGN were important players in the formation of galaxies. That's ongoing research. Virtually every galaxy, moderate massive galaxy, has a supermassive black hole within it. AGN are powerful celestial engines. I've done nothing else today. I think I've convinced you that they're very powerful, 26,000 billion suns worth of power. And they're something we've learned a great deal about, but which there is a lot of mystery yet. We don't know exactly the mechanism for feeding. We don't know how they interact with the galaxies as they form, and that connects with the history and evolution of the universe. And finally, Dr. Bottorff is crazy about active collective. Thank you very much for being patient. You can go if you want, but I'll entertain any questions. You can play Stumpy Chump if you want. Yes.
Just a minute.
No, they don't turn the same direction. They do have a spin, they don't turn the same direction, and they don't necessarily turn in the same direction as the galaxy that they're in. And in some cases, they're on their sides, and the ionization cone points out into the disk of the galaxy that they reside in. And so that tells you that various things have happened. They have not simultaneously necessarily formed. Maybe they form as a result of mergers, right? We now have seen black holes merge, smaller black holes merge, because we have the gravity wave telescope. So presumably these black holes grew by merger, because you can't just do it by feeding. It turns out it takes way too long to do that.
So if we know the galaxy is spinning in our galaxy, was that black hole stay in one spot?
No, the black hole is being carried along in the galaxy that it's in. The galaxies themselves are not expanding, but the space between the galaxies are. And so the black hole is going along for a ride with the galaxy that it's in.
But it stays in one spot.
It stays in one spot, right?
Thank you.
Yeah. Yes.
Just a minute. Hearing is not all that good. I did not hear you mention a black hole in our galaxy.
Yes, I did earlier with Andrea Getz. So she measured a black hole of 3 million solar masses, but it's not an active one. But it is there, and we detect its presence by stars in orbit around it.
Okay, I remember that, yeah. The other question is there only one?
Yes, but that's a good question, because there are galaxies where there's a couple of supermassive black holes.
Yeah.
And so they're slowly orbiting one another, and over cosmic time they will merge. So
Here only one.
here only one, that is correct. Yeah. Yes.
So what characterizes the difference between a supermassive and massive and a regular old black hole?
Okay, so regular old black holes are sort of like one solar mass up to maybe 80 solar masses, and there seems to then be a gap. There doesn't seem to be any 1,000 solar mass black holes or 100,000 solar mass black holes. So I would say that a supermassive black hole, just for practical purposes, starts at around maybe 500,000 solar masses. That's just a dividing line, because there's a gap. We haven't found these other objects yet. They ought to be there. And so that's a whole science question in itself. Why are there stellar mass black holes? Why are there supermassive black holes? Where are intermediate mass black holes?
Are there be black holes that are smaller than stellar?
Probably not, no, because I think it's the collapse of massive stars that result in black holes.
And that's the only black hole designation.
What's that?
And that's the only black hole designation is the shrinking of the stellar material.
Right, so
Astronomy wise, that's true.
right.
I've seen some papers written relative to gravity that is not astronomical in size, but that is smaller in size, but nevertheless have this crush.
Okay, so I've read about quantum black holes, right? And
that's
that,
wrong.
right. So I'm afraid I can't answer your question there, but I think quantum black holes are supposed to evaporate by something called Hawking radiation very quickly. So if you make one, you're going to go poof right away. There was some thought that there might be sort of smallish ones drifting several through our own solar system, and then we ought to see the sort of megaton level flashes, but they've never been seen. Question for the astronomer.
What's the relationship to pulsars?
So a pulsar is a stellar mass object. It is not quite a black hole, it's a neutron star. It's spinning very fast. It's spinning very fast for the same reason the ice dancer spins fast, because you go from a large thing to a small thing. Take something the size of the core of the sun and shrink it down to the size of Austin. And all of that spinning motion makes it spin very, very quickly. And because it has a magnetic field gathered together, like I was suggesting for my camp of the black hole wars, then the magnetic field gets twisted up and light gets beamed out along those twisted lines, which causes the pulsing effect of the pulsar.
All right, thank you very much, Dr. Boswell.
Thank you.
Let me finish this up. Okay. The microphone, please.
Thank you very much, everybody. You've been a great
Thank
audience.
you, Mark. We really appreciate it.